Okay, in this video I'm going to introduce the power rule for differentiation. So make sure you're up to date on that work on the difference quotient and the derivative. Remember we said that if y is equal to f of x, then the difference quotient gives me the average rate of change. The difference quotient is the change of y divided by the change in x. It's the average rate of change of y with respect to x, also known as the slope. The rise over the run. In function notation, that will be f of x plus h, subtract f of x all over h. Okay, and we've gone through all the visuals for this and all the work on functions in previous lessons. So I'm just going to focus in on the notation and then differentiating a couple of things. The derivative, which we call dy dx using Leibniz notation, is defined as being the limit as the change in x approaches 0 of delta y over delta x. Now the change in x here we call h the horizontal change, so that would be the limit as h tends towards 0 of f of x plus h, subtract f of x all over h. Okay, and that's what we know as f prime of x. So f prime of x is the derivative of f of x. dy dx is the derivative of y with respect to x. It all means the same stuff. Leibniz notation, function notation, different notations saying the same thing. Okay, the difference quotient gives me an average rate of change. The derivative gives me an instantaneous rate of change. And again, look back on previous videos and previous lessons on, all how this looks visually. The derivative gives me the slope of the tangent to the curve. So suppose I want to differentiate. Differentiation is the process of finding the derivative. So I want to take the derivative of x squared with respect to x from what we call first principles. So taking the derivative using, my definition of the derivative. So f of x equals x squared. We'll do x squared first. And again, remember what that means. If f of x is x squared, then f of x plus h, and the name of this function is f. If the input is x, well, the output is just the square of that. So if the input is x plus h, the output is just the square of that. Squaring x plus h will give me x squared plus 2hx plus h squared. So the derivative f prime of x is the limit as h tends towards 0. Let me just rewrite the definition here of f of x plus h, subtract f of x all over h. It's the limit as h tends to 0 of the difference quotient. In this case, well, it's going to be the limit as h tends to 0. F of x plus h in this case is x squared plus 2hx plus h squared. Subtract f of x. Well, f of x is x squared all over h. Now what happens here, and what should always happen at this point, is the original terms from the function, x squared, well, they shall cancel. So x squared subtract x squared giving me 0. So we get the limit as h tends to 0 of 2hx plus h squared all over h. And if we remember our work on limits, well, you sub in a value for h here, 0. You sub in 0, you get 0 over 0. That'll be an indeterminate form. That's a problem. That means the limit needs further work. And the further work here is just simplifying the fraction. So this will be equal to the limit as h tends towards 0. Dividing h into these, distributing it across the two terms, we get 2x plus h. Now I can apply my limit. Now I can sub in 0 for h. Once I sub it in, that disappears. That's just going to be 2x. So f prime of x is 2x. If f of x is x squared, then f prime of x is 2x. Okay? And there's my process. Remember what the function notation says. This just says the output is always the square of whatever the input is. So if x plus h is the input, we have to square it to get the output. And let's look at another example. X cubed. I'm going to take the derivative of x cubed with respect to x. So f of x equals x cubed. And remember what that means about f of x plus h. Well, this is just telling me to find the output, I just cube the input. I'd have to cube x plus h to find the output here. And if your binomial theorem is up to scratch, you should be able to do this pretty quickly. 3x squared h plus 3x h squared plus h cubed. And it's expected that you should be able to cube a binomial that quickly. Okay? It shouldn't take an awful long time. So we're going to look at the derivative. And again, let me write down the definition of the derivative. The derivative of f of x is equal to the limit as x tends to 0 of f of x plus h minus f of x all over h. That's the vertical change divided by the horizontal change. So it's the limit as x tends towards 0. F of x plus h here is x cubed plus 3x squared h plus 3x h squared plus h cubed. And then subtract f of x. Well, f of x is just x cubed all over h. And what should always happen at this stage is the original term or terms should cancel. So we get the limit as, so I should say h tends towards 0 as h tends towards 0 as h tends towards 0. That's my definition of 3x squared h plus 3x h squared plus h cubed all over h. And again, you sub 0 in here, you're just going to get 0 over 0, indeterminate form. That means my limit needs a little bit more work before I sub values in, and h can divide into each of these three terms. So we get 3x squared plus 3xh plus h squared. Now when I apply my limit, sub in 0, we'll be left with 3x squared. So if f of x is equal to x cubed, then f prime of x is equal to 3x squared. Remember, that tells me a way of finding my instantaneous rate of change. Let me just look very quickly what that means. If I was to graph f of x equals x cubed, and you can try this using GeoGebra, the graph looks like this. I just know this because I've seen it before. And if I pick, say, where the input is 2, well, the output here, if the function f of x equals x cubed, if that's my function, the output here will be 8, because cubing the input will give me 2 cubed, which is 8. So my point there on my function will be 2, 8. But what is the rate of change? What's the instantaneous? How is the function changing at this point? Well, it's changing in the same way that that tangent is changing at that point. And the slope of that tangent is equal to the derivative, f prime, at 2, the x value. And f prime is 3 times x squared, so this will be 3 times 2 squared, which would be 12. So the slope of that tangent line to the curve at that point would be 12. Okay? And that's what we mean by derivatives. So let me just write down a couple of little derivatives here, because I've done a lot of this stuff before. So let me just think about a function over here. I'm going to write out a table of values here. I'm going to write out a few of them. And at any stage, pause the video and see if you can write out the next few. But we've looked at x squared. We took the derivative there. That was the first one we did. The derivative was 2x. We did x cubed there, and we found the derivative was 3x squared. I could take the derivative of x to the power 4 using the same techniques. You're guaranteed to find it's 4x cubed. I could take the derivative of x to the power 5. I know it's going to be 5x to the power 4. So what about x to the power 6? Could you think about what the derivative of that would be? Well, it's guaranteed to be 6 times x to the power 5. because we have a power rule, which I won't prove, but you can prove with the binomial theorem that if f of x is equal to x to the power of n, well then f prime of x will be n multiplied by x to the power of n minus 1, always. So you can find the derivative of anything. You know, you want to take the derivative with respect to x of x to the power of 100. Well, I wonder, can you think what that is? It will be 100 times x to the power of 99. Okay, so we learn our power rule off by heart to save us going through all these steps. A little bit long-winded. It's very doable, of course, for simple things, but if you think about this 100 x to the power of 100, you know, raising x plus h to the power of 100 is going to give me an awful lot of terms. Okay, so I don't want to do that. So the power rule, once we can see the pattern, you hopefully can see what the power rule is. Okay. So let's look at that in action, and let's introduce a couple of more rules that are really just kind of very simple. And the first one is called the sum or difference rule for differentiation. And it says this. If f of x is equal to the sum of two other functions, g of x plus h of x, then f prime of x, the derivative, will just be equal to g prime of x plus h prime of x. And again, that's not just plus. If that was a subtraction, it would be the same thing. So let's have a look. I want to differentiate this thing, but I don't want to do it from first principles, so I'm going to get rid of that because that's going to take too long. I want to just use it by rule. So f of x is equal to x cubed plus x squared plus x plus 1. Okay, well, x cubed, the derivative of x cubed, if I take the derivative of this function, what we're going to get is the derivative of x cubed plus the derivative of x squared plus the derivative of x plus 1. And derivative of x cubed we found was 3x squared. Actually, we went through that from first principles earlier on. The derivative of x squared was 2x. And again, we went through that from first principles earlier on. What about these two, the derivative of x and the derivative of 1? Well, let me just take that away for a second and look at those individually. Suppose I want to take the derivative of x. Okay, the key thing to understand here is what's going on with the exponent. X is just x to the power of 1. And if I apply my power rule, that's going to be 1 times x to the power of 0. And anything raised to the power of 0 is 1, so that just becomes 1. And if I want to take the derivative with respect to x of 1, well, 1 is just the same as x to the power of 0. So we can write it as something with the base x. So the derivative with respect to x of x to the power of 0, well, that'll be 0 times x to the power of negative 1. But the x to the power of negative 1 doesn't matter because multiplying anything by 0 just gives me 0. So you should learn those two special cases by heart. Learn those, that the derivative of x is 1 and the derivative of 1 is 0. Let me come back to my problem. I wanted to take the derivative of x cubed plus x squared plus x plus 1. The derivative of x cubed, 3x squared, the derivative of x squared, 2x. The derivative of x, we said, was 1. The derivative of 1 is 0. That's my derivative. That's the sum or difference rule. Remember, that the derivative with respect to x of x is always 1, and the derivative with respect to x of 1 is always 0. Remember those two things, and then we can take the derivative of this. Remember also the power rule, that derivative with respect to x of x to the power of any number is equal to that number times x to the power of 1 n minus 1. Okay, of course, the variable we're taking the derivative with respect to has to be the same as the base here for this to work. So variable base. We look at one other rule called the constant multiple rule, and again you got to know these. If c is a constant and f of x is c times g of x, then f prime x will be c times g prime of x. That means we can always just factor out the constant and take the derivative of the x part. So let's have a look here. If I have y equals 5x cubed, subtract 4x squared, plus 3x, subtract 1. And I want to take the derivative with respect to x. Well, the derivative of y with respect to x is dy dx. Notice we're using Leibniz notation because it said y. In the previous example, we used function notation because it said f of x. So we've got a constant of 5 multiplied by this x cubed. So I can factor out the 5 and just take the derivative of the x cubed, which we know is 3x squared. And then I can factor out the negative 4 and just take the derivative of the x squared, which we know is 2x. And I can factor out the 3 and just take the derivative of x, which we know is 1. And I can factor out the negative 1 and take the derivative of 1, which we know is 0. So what I get is 15x squared, subtract 8x plus 3. Okay? Note, at this stage, the derivative with respect to x of any constant, anything that does not have a variable in it, is 0, not just 1. And learn that off by heart. Okay? So this is my function, y equals 5x cubed minus 4x squared plus 3x minus 1. If I was to graph that function, it looks something like this. Okay? And if I wanted to take, say, the point where x is 0, let's say 0, we'd have some point where x is 0. Now, I have no idea where that is on this function here. When x is 0, maybe it's over here, maybe it's over here. But if x is 0, the y coordinate would be 5 times 0 cubed minus 4 times 0 squared plus 3 times 0 minus 1. So the x coordinate would be negative 1. That's the y-intercept. That's a point. We could find the slope of the tangent at that point. The slope of the tangent is the derivative, dy dx. I'm looking for the slope. When x is equal to 0, I'm just going to write that using this notation. dy dx, vertical line, x equals 0, written down here. Well, that will be equal to 15 times 0 minus 8 times 0 plus 3. So that means the slope of the tangent line is 3 at the point 0, comma, negative 1. So it's either over here or over here. Okay, I don't really know where it is, but I do know wherever it is, if I draw the slope of the tangent, that slope of that tangent is going to equal to 3. Okay, maybe it's there. I don't know. I'm not going to investigate any further, but I could, of course, if I wanted to. Or it could be over here. The slope there would be 3. Okay, so that's differentiating and using the power rule. Okay, the power rule is given on page 25 of your tables, but the derivative with respect to x of x to the power of n is equal to n times x to the power of n minus 1. Remember, a power is just something to the power of something. This thing down here is called the base. This thing up here is called the exponent. You got to know all this terminology. If the base is variable and we take the derivative with respect to that variable, then we can apply the power rule, which is in here. Check it out. It's on page 25 of your formula and tables booklets. Okay.